Hello everyone, my name is Al-Munzir, and in this video I will be presenting and explaining the code for Lab 2 Part A and B. In this project we use the PIC16F84A microcontroller, which running at 4 MHz to implement two digital systems in MPLAB assembly. And both programs begin with the same configuration bits, and that is XTOSC, which selects the crystal oscillator mode to ensure the device operates with a stable external clock, the WDT, which disables the watchdog timer so the program does not reset unexpectedly, the PWRTE, which provides a controlled power-up delay to allow the voltage to stabilize before execution, and finally the CP, which disables the code protection so the program memory remains readable. To begin with, Part A focuses on creating a simple but effective 4-bit comparator. The microcontroller reads an 8-bit value from port B, where the lower nibble represents number A and the upper nibble represents number B. The code separates these two numbers by masking and swapping nibbles, which allows the PIC to handle both values independently. Therefore, the program can compare A and B directly using basic conditional checks. Based on the comparison result, one of three LEDs on port A is turned on. Green is turned on when A is greater than B, yellow when both numbers are equal, and finally red when A is less than B. Since the LEDs are active low, the program simply writes specific bit patterns to port A to activate the correct LED. Hence, the system continuously evaluates the switch inputs and visually indicates the relationship between the two 4-bit values, making it a practical example of simple digital decision making. Moving on to Part B, the second program demonstrates a timed up-down counter displayed on a common anode 7-segment display, showing how the PIC can perform tasks that involve timing, interrupts, and output formatting. The program sets RB0 as a direction control input, where a high signal triggers an upward count and a low signal triggers downward counting, while RB1 to RB7 serve as outputs to control the 7 segments of the display. Moreover, the timer 0 is configured with a 1 to 256 prescaler, which slows down the internal clock enough to create a predictable overflow rate of around 65 milliseconds. The interrupt routine counts a specific number of these overflows to build an accurate 1-second interval. So consequently, the counter updates exactly once every second, giving a clear, consistent output speed. Inside the interrupt, the program checks the RB0 switch to determine the counting direction, and then either increments or decrements the digit between 0 and 9, wrapping around when it reaches the limit. The updated count value is then passed into a lookup table that contains the correct segment pattern for each digit. Each pattern defines which segments turn on to display digits from 0 through 9, and since the display is a common anode, a 0-bit lights a segment. Meanwhile, the main loop stays idle because the entire timing, counting, and display refresh process is handled inside the interrupt mechanism, which runs autonomously in the background. And overall, Part A demonstrates how a PIC can perform basic digital comparisons and drive LEDs to represent logical relationships, while Part B shows how timer 0 interrupts, lookup tables, and I/O management come together to implement a functional real-time up-down counter. These two tasks, when combined, give a strong understanding of how microcontrollers handle input reading, decision-making, timing operations, and output control, which are fundamental concepts in embedded system design. Thank you for listening.